then as your magnitude grows, the weights, you have a better distribution over more bins, and then that would increase the entropy.
Doesn't
More randomness.
suggest that this methodology is flawed?
Well, it relies on bins, so that's the reason for the second experiment. Here they say, okay, deep linear networks, they're not what all of us are using, but their benefit is that we can actually have this formulation for mutual information. We don't need to bin or create any form of estimation. We actually, by making a noise assumption on the inside, you can just calculate it analytically.
So what was the noise assumption on the inside?
So that, well, first of all, they were feeding noise into this network, and the noise assumption here is that for the purpose of calculating the mutual information, we assume that the Gaussian noise is added to the hidden layer activity. So they kind of assume that there is some noise in the activity, which is already made out of noise.
But isn't that essentially giving you the same? The noise gives you a size of some sort, which is essentially making up the binning procedure by just replacing one length scale with a different length scale.
Yeah, so you are making assumptions that there are some sort of mixture of Gaussians inside your hidden activity. So they're kind of Gaussian bins, you can see that, but it's a much more robust estimation assumption rather than just cutting the space linearly.
I mean, it's a linear network, isn't it? Matrix multiplication is associative. So multiple layers in matrix multiplication can be represented exactly with a single layer, because you just multiply the matrices. And if you've got a convolution of noise, a Gaussian convolution of a Gaussian, a linear convolution of Gaussian, is another Gaussian. So I don't see what they gain in any way, shape or form by using a deep linear network.
I don't know. They cite research saying that deep linear networks are capable of showing sort of non-linear behavior, even though they are not as good as the networks that use standard non-linear.
Okay, they claim that.
Yeah.
Okay.
But they are still non-linear, right? Because they are ReLUs.
No,
They don't have
linear.
values.
Oh.
These are just matrix multiplications.
Yeah, that's why I think it's rubbish.
Yeah. They cite it's somewhere here. I can find you the paragraph where they do that. But basically, the conclusion from using linear networks is that they were capable to find networks that were generalizing but not compressing. So learns the map but doesn't compress. And at the same time, they use the same teacher-student setup and here with linear network and a hyperbolic tangent network, and they sort of forcefully put it in an overfitting regime, and so these weren't able to generalize, and this linear network doesn't have any compression, and this hyperbolic tangent function is compressing because we see sort of the leftward movement of these layer lines. And so that's the second experiment that says compression and generalization, they're not linked exactly, and that once again we can see networks doing their job without having any compression, which they also show here. This is the linear information plane for the first experiment. And then the third experiment, which I would say is my favorite because it's probably the easiest one, and I'm somewhat surprised that this experiment wasn't done by the authors of the original paper, but the idea here is extremely simple. They just don't use stochastic gradient descent, they use full batch. So they give a full data set to the network and ask the network to train, and the result of that is that this is stochastic and this is full batch on hyperbolic tangent, and this is the same but for ReLU. So we see that if we change from stochastic gradient descent to full batch, actually the mutual information picture doesn't change much. It's still doing the same thing. Actually, there's even more compression on the full batch here than on the stochastic one. So this is this kind of
Why would it be different?
Sorry? Why would it be different? Because the claim of the original paper was that the stochasticity of the stochastic gradient descent that injects the noise into our weights, and that leads to all this compression. So it was all this kind of pieces working together, and now piece by piece where they are doing that.
Excuse me, but wouldn't that stochasticity be in the data in the sense that if you were to repeat the whole setup a second time, then there would be variance between the weights you create, because your data would be slightly different, but you wouldn't. I don't think you would see it in the same setup with the same data.
Sorry, can you repeat the question?
This variance, right? That is variance you would expect between different runs on different data from the same source. But since that data is from different data from the same source with the same characteristics, but different realizations of the data. Whereas here you have the same data, just once you chop it up, once you leave it as a whole. I don't think these arguments would imply that there's a stochasticity in that.
No, but I think that, so the argument that the previous paper made was that because you are updating the weights by batch, every time that you run one epoch, you're going to get you would get more variance in the weights because of that, because you're running it one by one, and then updating the weights, and then running another batch and update the weights and run another batch.
Yeah, because there's research that if you make your batch smaller, your training will be even noisier. So because of the slicing of the data creates noise, and that's the noise responsible for the increase in the variance of your gradients, because they're kind of being pushed in different directions, and that just creates this diffusion behavior.
The noise per mean shift in one update, yes.
Yeah.
Over the whole thing, because the data only has so much information. I'm not sure about it.
Well, this is for sure. As you decrease your batch size, your training loss becomes noisier, so you have more variance in the training loss.
Between the batches.
Yeah, these classical pictures of when you do stochastic gradient descent on the optimization plane, you see this zigzag behavior. That's noisy. But if you do full batch, it will go straight to the the bottom of the optimization landscape, because it knows exactly where to go. We use stochastic gradient descent.
Yeah, but if the batch is appropriately sized, but it's true. But at the end, it's always an approximation of the full batch.
Yeah.
But if
Yeah, exactly.
Function. So if I don't see, I'm not surprised that the relative entropy between layers doesn't change much.
Oh, it depends on your data set, because that depends on how smooth your data is, so to speak. So that if you take the batches, that they will actually resemble the full batch.
But
That is not always the case. Yeah, it's true. That is not always the case.
And it's not just the data set, you can also smooth out your optimization landscape with like regularization or normalization things that helps you to...
But there you actually add additional information, right? Whereas the batching, I think why do we batch? I think we mostly do it because computational limitations. Because
not always. So we don't do full batch because sometimes that would leave you in a local minimum, because optimization problems in deep learning are non-convex. So